Hello, we are from Group 4. This is Group 4 member, which is my name is DOSSIMON LIANU, and the other member is DARIEN, Ellen, Kuhan, and CHANTY. So, the assignment is as a part of Corporate Social Responsibility CSR activity under Mechanical Engineering Program, Faculty of Engineering, University of Malaysia Sabah. Your group have been sent to a rural village in Tamunan to set up a small-scale electrical power system for the villages. They want to use the photovoltaic system to power up the light and fans in the common hall. Your task is to come up with the design of the electrical power system, which is 230 volt AC output. Prepare a comprehensive report, discuss the design, which may include load assumption of the light and fans, equipment requirement, and the overall costing, circuit diagram, process and operation, safety precaution or protection, impact on environment, and calculation. So the first one is load assumption of the light and fans. The common hall have 20 meter for the width and 35 meter for the long and 20 meter for the height. So the first one, we use the light, which is we use LED high bay light. We use 10 light to light the hall. Each of them have power consumption 100 watt. So the total power for the light is 1000 watt. For the fans, we use wall mount fan, and we use 8 fan. Each of them have power consumption 180 watt. So the total consumption for fan is 1440 watt. So the total load for the light and fans is 2440 watt.
Good day, sir. My name is CHANTY SYMUS with matrix number BK21110272. Today, I will be presenting about the equipment requirement for the photovoltaic power system. The photovoltaic power system consists of 4 main components, which are monocrystalline solar panel with 200 watt and 24 volt, 80 ampere solar charge controller, capacity lithium battery 24 volt with 150 Ah. Last but not least, inverter with 24 volt to 230 volt output. Based on this equipment, some calculations have been made to find the right specification of each main equipment. This is the formula and calculation involved. First, to find the suitable solar panel, I have conduct calculation to calculate the system size based on the daily load assumption of the common hall, which result in 5439 and 72 watt. Hence, from this value, we choose the monocrystalline solar panel that have 24 volt and 200 watt. This solar panel then will be constructed in parallel to achieve the required power assumption. The solar panel then will be constructed in parallel to achieve the required power to cover up the load assumption. Next, to find the suitable charge controller, we first divide the total watt of the solar panel, which is 5400, with the battery bank expected voltage value, which is 24 volt, resulting in 225 ampere. The solar charge controller ampere or current should be equal or greater than the 225 ampere. However, there are no available 225 ampere solar charge controller. Hence, total of 380 ampere solar charge controller is constructed in parallel to be able to handle the current from the solar panel. Last but not least is the battery. To choose the right battery, we first have to conduct some calculation to determine the battery bank size. With the shown formula, which give the value of 91.296 kilowatt per hour, this value would help us to find the ampere hour that is suitable for our battery. The ampere hours that we get is 3804 Ah. Therefore, capacity lithium battery with specification of 24 volts and 150 Ah are chosen. Total of 25 batteries will be connected in parallel to each other to achieve the required 3804 Ah that needs for the common hall. These are the total costing of our photovoltaic system. The overall equipment consists of solar panel with 200 watt and 24 volt, mounting structure 40 mm, mounting bracket, charge controller 80 ampere, battery 24 volt with 150 Ah, inverter, wires 15 meters and 6 mm square, and lastly the screw, which conclude total of 150,171.7 ringgit Malaysia for the whole photovoltaic system.
Hello, Sir Azri. So now I'm going to explain about the process and operation of our system. So first of all, the photovoltaic panels captures sunlight and converts it into a DC current, which is direct current electrical power. The resulting DC power is then directed to the charge controller, a crucial component overseeing the charging process. This controller prevents battery overcharging, ensuring optional charging condition and prolonging overall battery lifespan. With the charge control mechanism in place, excess energy generated during the day efficiently accumulates in the battery, serving as a dependable energy reservoir. This stored energy becomes a reliable source, providing continuous and stable power during periods of low or no sunlight, addressing the energy needs of the community. Which means when there's no current or no sunlight, so this will come in hand in order to provide the current. So to meet these specific power requirements of the rural village common hall, the next step involves converting DC power into alternating current, which is AC current. The inverter takes the stored DC power from the battery bank and transforms it into AC power with a 230 volts output. This AC power is well suited for operating lights and fans, essential appliances within the communal space. During the illumination phase, AC power is directed towards energy-efficient lights in the common hall, fulfilling the community's lighting needs during evenings and nights, thereby enhancing safety and overall quality of life. For ventilation and cooling purposes within common hall, fans comes into the operation directly powered by the battery, providing a continuous flow of air and contributing to the comfort of the residents. In this figure 2, the figure 2 illustrates a DC to AC circuit facilitating a connection between the deep cycle battery bank and the inverter. The inverter plays a crucial role by converting DC power stored in the batteries into AC power. Thereby, this provides a suitable source for operating standard electrical device and appliances within the common hall. An inverter circuit is designed to transform direct current, which is DC power, into alternating current, which is the AC power. This circuit is particularly advantageous for generating higher voltage level from a lower voltage DC supply such as a battery. While DC converter circuits can serve a similar purpose, they are constrained by specific voltage limitations. The inverter circuit, which converts a 12 volts DC input into a 230 volt AC output, is constructed using the IC CD4047, which is a model name for a pulse oscillator for switching. The N-channel power MOSFET IR FZ44N serves as the switch in this configuration. Additionally, the secondary transformer operates inversely, functioning as a step-up transformer to convert low AC voltage to a higher AC voltage. The 10 and 11 pin outputs of the IC directly control the power of MOSFET, arranged in a push and pull configuration. It is crucial to utilize suitable heat sinks for the MOSFET due to significant heat generated. The output transformer features a 12-volt, 012-volt, 1 ampere secondary, and a 230-volt primary. So now I'm gonna explain about the AC distribution circuit. So this is figure 3, which shows the AC distribution circuit. This transports electricity from the inverter to the electrical loads in the common hall. So the inverter is the red color component that is drawn in the diagram. So okay, this inverter will transport the electricity to the electrical loads in the common hall, including lights and fans. So in this case, after doing some research, we have decided to include 10 lamps and 8 fans for the common hall.
Good morning, Doctor. I'm Alan Hall, and I will now to present the safety precaution. And the safety precaution consider electric safety, battery safety, solar panel safety, system monitoring and control, community training, and compliance and certification. The first one, the electrical safety. We can use the high quality wiring with proper insulation to prevent electrical shocks and short circuit, and install the circuit breakers, fuse and isolation switch for overload protection and secure maintenance. Implement a grounding system to redirect the electrical fault safety into the ground is also a ways. And lastly, for this one is a clearly label all the electrical components for easy identification to avoid to avoid any mistaken. And the second one, the battery safety. Place the batteries in well ventilation area to dissipate heat and prevent gas buildup. Securely mount battery to prevent movement or tipping. Establish routine maintenance guidelines including electrolyte levels check and connection tightening. And the last is implement protection measure against extreme temperature. And for the solar panel safety, securely mount solar panels to withstand environmental conditions. Exercise precaution during installation or maintenance to prevent electrical shock. And we have to consider fire safety risks associated with the solar panels. And the fourth one, system monitoring and control. We we can integrate remote monitoring capabilities for issue detection without physical intervention. And we can also install an emergency shut-off mechanism for quick system disconnection during the emergencies. And the fifth, community training. We can we must conduct training sessions for local residents on basic electrical safety practice and emergency procedures, and it can make sure that they know what they should do during the emergency happen. And we have to provide detailed documentation on system operation, maintenance, and emergency protocols. And this can refer to the residents. Uh, this can refer to the residents so that they know how to use the system correctly. And the last one is a compliance and certification, and it can ensure compliance with local electrical and safety regulation. And lastly, we must use certified components following industry standards so that it is as an insurance to use the tools. And I think that's all for my part. Thank you.
My name is DARIEN, and now I'm going to talk about on adopting solar energy, which is a major driver of the transition to a sustainable and more brighter future. So, the significant decrease in our carbon footprint, which is a vital first step in addressing the global issue of climate change, is at the forefront of this paradigm shift. Solar energy generation, it produces clean electricity without producing appreciable levels of carbon dioxide, which is a shining example of environmental responsibility in contrast to traditional resources such as coal and gas. This prepares the ground for a more robust and sustainable energy landscape while also addressing the pressing need for decarbonization. So, making the switch to solar energy has repercussions that go beyond lowering emissions and include protecting our limited natural resources. Because of this limited supply, fossil fuels endanger the delicate equilibrium to our ecosystem. Solar energy, on the other hand, makes use of the sun's boundless power to provide a sustainable and renewable alternative that lessens the burden on the planet's resources. This change supports a regenerative approach to energy generation and protects against the resource depletion, bringing our trajectory into line with ecological balance and responsible management. Then finally, focusing on the immediate effect, solar system deployment becomes a prudent and environmentally conscious course of action. So these systems can be carefully incorporated into current landscapes with a comparatively modest footprint, reducing land utilization and possible habitat impact. In addition to addressing environmental concerns, this strategic placement emphasizes on solar energy infrastructure which is compatible with biodiversity and ecosystems of the areas that is located in it. So that's it from me. Thank you.